Now the first example is the laminated core iron losses calculation. We will simulate the transformer. The transformer consists of the winding, the primary winding, the secondary winding, and the core. The core is made of iron 5 electrical steel. Our task is to calculate the core losses. Transformer operates at AC current at frequency of 400 Hz, and the core losses are caused by the alternating magnetic field. So our task is to calculate the magnetic field distribution in the core. We will simulate the simple case, the no-load operation. The no-load operation means that there is no load connected to the secondary winding. So there is no current in the secondary winding, only primary winding carries the electric current. Each winding consists of multiple turns. The primary winding has 324 turns. In the model, we will not draw each turn. Remember, our task is to calculate magnetic field. And to calculate magnetic field, we can represent the multi-turn winding with just square block and specify the total current in this block. This total current is equal to the product of single turn current and number of turns. We will simulate this case as two-dimensional. The core is laminated, which means that it is made of insulated sheets of metal. So there is virtually no current in Z direction. Z direction points behind the screen. So eventually we will specify zero electric conductivity in the core, but still there are losses in the core. There are losses. You can follow this link to the Arnold Magnetics website. And check the steel data. These are the experimental data, and you can see indeed there are losses. The x-axis is the core loss and the y-axis is the magnetic flux density. And each line corresponds to the different frequency. We will simulate this case, 400 Hz. The source of these losses are different. There are eddy current inside each sheet. Inside each of these sheets there is eddy current. And there are also the hysteresis losses. Now let's start QuickField and simulate this case. The model is simple, so I will draw it from the beginning. I will create the new problem. And call it core loss. The problem type, I choose the AC magnetics. The transformer, remember, operates at 400 Hz. The model class is plane parallel, which means that I will only draw the cross section of the transformer, like you see it on the screen. So, problem type AC magnetics, model class is plane parallel, and the frequency is 400 Hz. This is the geometry model editor window, and here I should draw the geometry model. The core dimensions are 60 by 60 millimeters, and the leg width is 10 millimeters. So I will switch to millimeters, and insert the rectangle. And this is the core. I will move it by 10 millimeters. And I need to add the central leg. Now I will remove unnecessary lines. And here you can see this is the core. Next I will add the winding. There are the faster way to create the geometry model. You can import the geometry model from the DXF. But for simple cases, you can use QuickField. Now this is the primary winding. The direct current, the back current, and this is the insulation layer. We simulate the no-load mode, so I do not draw the secondary winding. Now the next step is to, after we finish drawing the geometry model, is to assign properties for each object. To do it, I simply select the object and open the properties dialog. And here I type in the name of the object, core. The name then appears in the tree. This is the primary winding positive current. and this is the primary winding negative current, back current. And this is the insulation. And here is the place for the secondary winding. I will give it the label, but assign no electric excitation. Now here the objects in my model: the core, the insulation, primary winding, secondary winding. And I will assign zero magnetic flux on the external boundary. In fact, the magnetic flux flows in the core. It doesn't come outside the core. So on the core surface, I specify zero magnetic flux. Now we have finished giving labels to geometric objects, and now we should assign physical properties for each label. For the insulation, I assign the magnetic permeability of 1. For the secondary winding, I again assign the magnetic permeability of 1. And I do not assign any current source in the secondary winding. For the primary winding, I specify the magnetic permeability, and I specify the total current. As I said, the total current, the current of this single turn is 16.5 milliamperes, and there are 324 turns. Now let's resize the window so we can see the data. Total current 6.5 milliamperes multiplied by number of turns. You see, QuickField supports equations. And for the negative current, the same, the magnetic permeability, and minus 16.5 times 10 to the power of minus 3 multiplied by 324. Now that's for the winding and for the insulation. For the core, you can specify magnetic permeability or the curve. If you check the material data at the Arnold's magnetic website, you can see you can find the magnetization curve. So this curve should be specified in the material properties. So well, this is the data. If we convert the Gauss to Tesla, you will get 0.2. And if you convert from oersteds to amperes per meter, here is the value. Now let's copy the value from this data file to QuickField. Here you can see the BH curve. Now that's more simple. The new feature of QuickField 6.2 is that you can specify the core loss coefficients. How can you get these core loss coefficients from the experimental data? The Arnold magnetics provides only these data. How to calculate the coefficients? Well, you can do it in Excel. And here you can see this is all the original data from this chart. Then I converted the losses from watts per pound to the watts per meter cube. And from this data, you can calculate the coefficients of Bertotti equation. Now this task is automated. We prepared the free tool you can use to calculate the coefficients, these three coefficients, from experimental data. Just press the button. You see these lines are approximation of the experimental data. Now, where can you get this tool? You can open our website, follow to download free tools section, and here it is, core loss coefficient calculator. Now let's return back to QuickField. In QuickField, you should specify these three coefficients. So here I type 123.1, 0.06, 1.9695. That's all. At the external boundary, as I said, we specify zero magnetic field. Now let's build the finite element mesh and run the simulation. Here you can see the magnetic field distribution in the single-phase transformer in no-load mode. There is electric current in the primary winding. Now let's calculate the losses. To calculate the losses, you should first select the object where you would like to calculate the loss. I select the core. Next, you can open the integral calculator tab and choose the integral value, the core loss. And here you can see are the core loss in a transformer. Please remember that this is the two-dimensional model and the core loss are calculated per 1 meter of transformer depth. The Z length of this model is 1 meter. Of course, you can adjust this length to the real one. This transformer has the depth of 220 millimeters. These are the magnetic losses in the transformer. The transformer is very small, 60 by 60 millimeters. These are the core loss in no load mode. And of course, you can then create the thermal analysis problem and run the multiphysics analysis. You can export the losses distribution from the core, from the magnetic problem in the thermal problem. In fact, the losses distribution is not uniform. I will adjust the field picture and show you the magnetic losses distribution. You see, the losses are concentrated in the place where the flux density is high, and the losses are very low in the places where the flux density is low.